best thing to do in that state is. All right. If you're presenting an approach, always good to compare it with another approach. So we came up with another approach as well, which was a heuristic solution. This one's pretty easy. It says if the person's here and they're facing this direction, we're going to assume they're going to keep on walking straight. So if they walk straight here, we'll place a robot over here and then direct them to the goal over here. So this node 1 is the shortest, is the closest goal in this entire path we think they're going to follow. And we point them towards the goal over here. All right. Finally, we had a bunch of different maps that we want to evaluate this approach on, and this is what they look like. This is what the results came out. To compute the results, we did two different studies. We had real humans control our avatars inside a simulator to see which approach was better. We also had a lot of tests with an artificial agent that follows the same policy, same human motion model that we've hand coded up. So basically, what that means is that the value iteration solution is optimal in each of these cases. So the heuristic can never beat it. We know this for a fact. It's a question of how much difference there is. So when you have a simple grid-like environment like this on the left, what you notice is that there is very little difference between the heuristic and the value iteration policy because it's very easy to solve the problem, even if you come up with a heuristic that does it. When you have more complicated environments like the other two, it becomes much more difficult, so the gap between these two guys becomes larger and larger. All right. So this was also fun. This was basically where we had an experiment. This is the same video I showed you at the beginning of the talk. It's where a human controls an avatar and they follow the same policy we've described. What this means is that because we've used our hand-coded human motion model to train the MDP, to solve the MDP, it's no longer obvious that we're getting the most optimal solution out of it. And the reason for that is the human might actually be following a different model for their motion. So for instance, if I'm telling the human to go there, but the human always goes left, that's really hard to code up beforehand. So you need to have an idea of how the human's going to behave when you have these robots in the environment. So what this means is that our policy is no longer optimal, but in general it does better every time in all these different instances that we tried. All right. So I've really rushed over the details, so if you have any questions, we can go over them now. But in conclusion, what this work does is it introduces multi-robot human guidance as a Markov decision process. So I should mention we didn't come up with an algorithm for solving Markov decision processes. To solve this problem, all we had to do was formulate it as an existing Markov decision process and use existing tools to solve this problem. The MDP formulation uses a graph of the environment. And in the paper that I've taken this work from, we describe how that graph can be generated as well. And using value iteration and this reduced problem where we don't worry about how to actually move a robot to a given location, we just teleport them into place. The optimal solution for this policy can be solved using value iteration. And we've used hand-coded human models, hand-coded human motion model in this work. And all the code is up on GitHub. I still need to produce better documentation for this. Documentation is always an issue when you're working alone on a project, but I'll try and get this up at some point of time. But we've used RAS and Gazebo quite heavily for this project if you're ever interested in looking that sort of up. And that was basically it for today. So time for any questions? Yep, go ahead.
So if the human keeps taking wrong turns, keeps going in the wrong directions, you keep getting negative rewards, right?
Yep.
So would the robots act any differently the more negative rewards you get?
So the way this normally works is I've used something called value iteration, where if I know how a human is going to behave with those robots, when the robots is presenting it. So let's say, let me backtrack that. So a robot is saying, go over there, and I've made some assumptions as to how a human is going to behave when the robot says go over there, right? If those assumptions are not correct, you need to do something called reinforcement learning, which is where you don't know how the environment is going to change when you run a particular action. So what you'll do is that if you perform an action, you also try and figure out how the world is going to change because of that action. So what that means is that if I have, like my person is making very, very incorrect decisions, the system will actually learn over a period of time that, when I say go over there, like the person goes over here, so I should probably, go tell the person to go over there, and that's how they'll actually end up going over there. So the system can actually learn that. It'll be very, very slow because, these are like, I don't know, it's a very, very huge state space over here. So right now I assume I know how a human is going to act. But if I don't know how a human is going to act, you have to also learn how a human is going to act in the environment, whereas at the same time you're trying to figure out what the value of each state is. So it's a much, much slower process than what I've described here. But yeah, that's a great question. Anything else? Yeah.
So earlier when you said that in Gazebo you just teleport the robots to where they need to be, was that the same for the thing when you showed the statistics of how yours performed versus the heuristic?
Yes. So this is all using that same teleportation. Okay. So I should mention that these first results, I haven't explained what the different number of robots here is, but that's don't worry too much about that. This was like, this doesn't even need a simulator, right? Because we're using an agent which which follows the human model that we've described in our. Right. So you don't even need to simulate it out. You know exactly how they're going to act. Okay. This graph, the second result was with the simulator, so we were teleporting them into place. And we already have some work in place where we don't teleport the robots anymore. We actually have to physically sort of move them and wait for them to move around in the environment. The only problem is that because the state space becomes so huge, you can't actually run value iteration anymore. So you can't get the optimal policy out. So we have to use different, we've used approximate Markov decision process solvers to solve that problem. But yeah, I'll let this video play in the background, I guess. But yeah, any more questions? Oh yeah, go ahead.
Is this only accounting for one human at a time, or can it be multiple people?
That's another great question. This system is accounting for one human at a time, and accounting for multiple people at the same time. If you want to use the exact same framework, it just like explodes your state space, because there are like, it's a combinatorics problem. Like there are so many choices I can have for these state members. And now if you have another person in there, then there are so many other choices I can have there. So it just explodes the state space completely. So value iteration is probably not going to converge over there. But yeah, this problem, what I've described, it doesn't solve for multiple people. You can trivially apply it for multiple people by, if you have 10 robots free and you can teleport them anywhere, you can run both of them in parallel without, interdependence. But that's not what's going to happen in the real world. Like in the real world, you're going to probably be moving a robot into place. But if you're moving a robot into place for the first person, you can't move it into place for the second person, and so on. So that's definitely something that needs to be solved when we implement it with either real motion or real robots. Yeah. All right. Any last questions? All right, that was it. Thanks for listening, guys, and hopefully I was successfully able to teach something today in the talk as well, so that's always nice. But yeah, if you have any questions about this, let me know. Oh, I guess I do have one last video to show, which I forgot to show earlier. So a different line of research that I didn't mention today was we are also trying to do single robot task planning, which is basically, how I described this whole Markov decision process. So that's really hard to describe all the time, like from scratch. Like I don't want to specify each state and each action for these states. So you can come up with some general descriptions and use automated planning tools to form this Markov decision process and solve them. So this is like one such example where we want a robot to deliver coffee, always a useful task to work on in the CS building. But let me see if I can turn the volume up. So my speakers are fairly loud. I think you might be able to hear it. But this is the robot completely autonomously navigating on its own. Bring the camera close to the laptop. Oh, I think I'm going to allow it. So this is the robot going to the coffee shop and asking for a mocha, which is like comes up on the display here.
One smoker has been loaded.
it took us like, this is not a final video we're gonna make of this, but this is like sort of, we realized too late we wanted to make a video of it. So now you'll actually see the coffee shop and the, so this is inside the Computer Science Building coffee shop, and then it goes, huh?
Was this today?
A week ago or something like that.
I saw them hanging out there today with that robot.
Oh yeah, there are a lot of freshman students from the FRI program are also working on it. But then it goes to a table, asks you to deliver coffee, and the coffee shop was actually closed because we would do all our work after 7 p.m. But it asks you to remove the mocha, and then you hit done, and then the robot goes to deliver another coffee, still completely autonomously. The biggest problem with running this robot in the atrium is like, you'd expect people to get out of the way. They don't get out of the way. They want to stand in front of it and see if it goes around them. it'll do that, but like not something, we want to overly test.
With an empty car or something.
So you're using the RAS navigation stuff too?
Close to it. I'm gonna let this play out without volume, actually. What we have is, we have most of the ROS navigation stack. We rewrote the local navigator. So there are two components to navigation in general. One is the global planner. It's like, this is the path I want to take to the goal, and then you have to execute that path. So we rewrote the local version, which is how you execute that path, because we were able to get something far smoother than the default navigation stack. Right. But this is also something we're interested in, so next we're going to try and get our robots to go up and down on the elevator. They don't have any hands to press any button, which is really annoying. Well, there's certain advantages to it. You don't really want to figure out how to get a robot to press a button, because that's difficult. That's a difficult problem to solve. So we're going to try and get it to go to people and ask for help pressing the buttons and see if that works. So that's also going to be